Now that we've had the chance to talk about the continental shelf, let's turn our attention to the continental slope. Again, the continental slope is between 4 to 6 degrees slope, like a steep road, something that you might run hill repeats on. It's a narrow region between 10 and 100 kilometers and well below storm wave base. So this region is dominated by density currents. The major types of sediment structures that we're going to see here are formed by debris flows and contour deposits. We're also going to get turbidites that form on the slope, travel down the slope, and get deposited on the continental rise. These sediments are going to pile up on the rise as submarine fans. The continental slope is also bisected by submarine canyons. You're probably familiar with Monterey Canyon here off the coast of California. Next week, we'll talk about the abyssal plain. So the slope region is dominated by sediment gravity flows. So you might want to refer back to the sediment gravity flow lecture if you've forgotten some of the key characteristics of these deposits. Debris flows are our sediment-rich sediment gravity flows. Debris flows, or the debriites, are going to be matrix supported if they're muddy, and these we call cohesive debris flows. They'll be grain supported if they're more sandy or gravelly, and these we call grain flows or cohesionless debris flows. There's no cohesion because they're not muddy. This diagram is giving you an idea of how a sediment gravity flow might get started on the slope. The continental shelf might collapse at the edge, and the loose sediment on this steep slope is unstable and will begin to slump down the slope and can form a sediment and water flow. These could be our debris flows, or if they're more fluid rich, they'll be our turbidity flows or turbidity currents, which we've spoken about before. If fluid turbulence, you can see the turbulent eddies here, support the flow, then these are going to be our turbidity currents, and they're going to form turbidites. They could be muddy with more laminar flow, or sandy if they have more turbulent flow, where the sediments and fluids are mixed together. So don't forget what we've learned about our Reynolds number, where density, the fluid velocity, and the length or distance that the flow is traveling over the viscosity determines whether or not we have laminar flow or turbulent flow. If viscosity is greater than the inertia of the sediment, we'll have laminar flow. If the inertia, so this motion of all of the flow, is greater than the viscosity, then we're going to have turbulent flow. And that inertia is going to be dominated by density, fluid velocity, and the length of the deposit. So again, the turbulent flow is going to be where we have a mixing of fluids and sediments, forming these turbidity currents. So what's going to get these sediment gravity flows started on the slope? There are a variety of processes that might initiate a sediment gravity flow. One of those is sea level change. So as sea level might rise or fall, you might disturb some of the sediments on the slope, especially if you have a sea level fall and you start to erode some of that slope sediment. From a eustatic low stand, if sea level falls because more water is stored up on the continent as ice, you could have a low stand and start to erode some of that slope sediment. Or if tectonic processes uplift the slope deposits, bring them up higher, again, you'll get more erosion because you're moving the slope sediments now into a zone where storm waves or fair weather waves might interact with them. And again, that can disturb the slope sediments and send them down the slope to form these gravity flows. Another potential process, number 2, is the proximity to canyons. If there are submarine canyons that cut through the slope, those can be a conduit by which sediment will flow from the shelf out onto the continental rise. If you get a lot of sediment building up on the continental shelf and the margin of the slope, it will eventually collapse down onto the slope and continue to flow down the slope out onto the continental rise. A major earthquake can also displace the unstable slope sediment. So it will send that sediment as a landslide slumping down the slope and can also initiate some of these sediment gravity flows. And finally, the migration of sheet sands and channels could also change how sediments are moving around on the basin floor and initiate some of these sediment gravity flows. We've talked about a variety of deposits in the past, and there are some particular terms that we could learn to describe these deposits. Things like olistoliths, olistostromes, and slump deposits. Our olistoliths, lith is for rock, are those that are dominated more by pieces of rock that you can see here in a rockfall deposit, in a sliding deposit where we have a landslide, a whole chunk of the mountainside or of the continental slope slides away together as these cohesive blocks, or in a debris flow where we have particular blocks of sediment. Compared with some of these slump deposits, which we've seen in the past, where we have these bedded or laminated sediments that are folding on top of one another, seen here. And then we have our turbidity currents, where suspension is mostly due to the fluid turbulence. So you're already familiar with these ideas, but this is just another way to look at all of these different sediment gravity flows and the kind of deposits that they form at the end. There's a little bit of a continuity here that we haven't really talked about before between debris flows and turbidite deposits. And this is really made more evident in the deep water systems that we're discussing. Because there's so much fluid available, of course, under the water, in the ocean, in the deep ocean, we can have this transition from a debris type flow to a more turbidite type flow if more water and fluid becomes entrained in and among the sediments. So in this figure here, we're seeing this cohesive debris flow. So remember, cohesive means there's a lot of mud involved, and a debris flow tends to be matrix supported. Again, that mud is providing the matrix strength that is carrying all of the large sediment particles. And in general, these debris flows are dominated by more laminar flow type behaviors. The L that you see in that cohesive event type stands for laminar flow. Then there's a little bit of a hybrid between something that has some laminar flow components on the left-hand side and then initiates more turbulent flow out in front of the laminar flow deposits. So here we have a combination of turbulent and laminar flow. And then, of course, the turbidity currents, the turbid flow, is non-cohesive. So there's not a lot of mud involved in the formation of these turbidity currents. They're more sand dominated. And the process by which these turbidity currents form is through turbid flow. So again, the eddies and the turbidity of the water is what is propelling the sediment, as well as gravity pulling that sediment down the slope. So this is in contrast again with our debris flows, which have a matrix strength because of the clays that are able to support the larger clasts, and the whole thing is moving down slope due to gravity, and it's more of a laminar flow. We saw that behavior in some of the videos we watched in debris flow, where they tend to move just like a wall. There's not a lot of turbidity happening. Compared to the turbidite deposits, which have a lot of fluid entrained among the sediment and the turbidity of the fluid is causing the continued suspension and motion of all the sediment particles. Again, this figure is representing some of this continuum between turbidity flows, concentrated density flows, and hyperconcentrated density flows. I don't want to get too deep into this, but just to recognize that there are different hypotheses about the amount of, for example, fluid turbulence, grain-to-grain interactions, and matrix support that's going to occur between the more debris flow type deposits on the left, these intermediate deposits here that maintain momentum through these grain-to-grain interactions, and the fluid turbulence driven turbidity flows. You'll see some of the other things that differ between them are the flow velocities. Here, these are slower, these are the most rapid, and these are sort of moderate. Here, the sediment concentration. Remember that these are matrix supported, so there's a lot of sediment involved here. Here, there's a lot more fluid turbulence and less volume of sediment. And finally, the deposit thickness as a fraction of the flow thickness. The debris flow itself tends to freeze, and so the thickness as it's moving and the thickness of the final resting deposit are about the same. Versus our turbidity flows, where the sediment is suspended and flowing in the turbidness of the water, and as it settles out, it forms a much thinner deposit than the actual flow of all of the water and sediment combined. So if you wanted to compare a debris flow to a turbidite, you might say that some of the top deposits, the final settling deposits of a debris flow, could be kind of equivalent to the basal deposits of a turbidite sequence. It's also too important to remember that these debriites and turbidites that are forming on the continental slope are events, right? We talked about some of the triggers for these events. And in between them, we might expect to see a lot of mud deposits from muds that are settling out of suspension because, again, we're below fair weather wave base. So we're gonna take a pause right here and watch some videos of turbidity currents that form on the slope. And in particular, we're going to look at turbidity currents that have been observed right here in Monterey Canyon. So once all of that turbulent flow stops moving and the sediments begin to settle out, turbid currents tend to form a sequence, sometimes referred to as the Boma sequence, for the person who first described these layers of sediments that are found next to one another. The Boma sequence is described by 5 particular facies. The first facies, the A facies, is made of structureless or graded, normally graded with the coarsest material at the bottom and fining upward. This is interpreted to represent the upper flow regime. Remember, Froude number greater than 1, and it represents really rapid deposition. That would explain why it's massive. There was no time for Stokes' law to allow for the settling of the largest particles first. If it settles a little bit more slowly, then we might get that normal grading that's seen in some turbidite sequences. The B facies is represented by parallel laminations, and is thought to represent the upper flow regime and deposition in the plain bed. The C facies has both sand and silt, and this facies is found with ripples and wavy or convoluted laminae. And it's thought, therefore, to represent the lower flow regime, right? Because if we have ripples forming, then we know we're in subcritical flow in the lower flow regime. The wavy or convoluted laminae can be from all of that silt and sand coming out of suspension and forming underneath this current, and there's so much sediment being deposited that it can become a little bit slumped and you get that convoluted laminae. The D facies has more silt and it has parallel laminations, but the interpretation isn't quite clear. Is it the lower plain bed? That doesn't quite make sense. So it's a little uncertain exactly how that unit forms. And then the E facies represents massive or graded, fine-grained, low-density turbidity current deposition, followed by pelagic sedimentation. So the background sediments or muds that fall out of suspension in the meantime in between these turbidity sequences. So the facies A, B, C, and D are formed as a result of that turbid current, and then the E facies happens as mud settles out of suspension after the event has passed. We can look at this on our bedform stability diagram. That A facies representing the upper plane, the upper flatbed, in this upper flow regime, Froude number greater than 1. The B facies, again, representing upper flatbed deposition. And then the C facies, where we start to get ripples, moving into the subcritical flow. The D facies doesn't necessarily fit very well in this bedform stability diagram. It doesn't go back into the lower flatbed because this would indicate coarser grain material, but instead we know that we're moving toward finer grain material. And then the E facies represents mud that's settling out of suspension in between turbidity current events. Fleesh, you might know the word, is layers of turbidites. So you'll get these repeated turbidite sequences that form on the slope out onto the continental rise. So you'll see these stacks of turbidites in certain deep water environments. The other process that's really important on the continental slope are the currents. There are contour currents that are moving between 5 and 20 centimeters per second, and they form contourites, which is the resedimentation of hemipelagic mud as a result of the change in velocity as these currents come through and disturb the sediments that have been deposited on the continental slope and the continental rise. So we're going to take a moment right now to watch some videos on what causes currents at the bottom of the ocean.
This is Making Waves from NOAA's National Ocean Service. In today's episode, what are ocean currents? Now, the ocean never stands still. Even here in this quiet marina, you can see the water is slowly moving. If you stood at this spot for many hours, you'd witness the rise and fall of the tide, caused by the gravitational pull of the moon and the sun on our planet. But what's causing the motion you see here with this gently swaying anemone on the seafloor off the Atlantic coast? This is ocean current. The reason we have currents in the ocean is a bit more complicated. Let's go back to the shoreline to witness one cause of ocean currents: the tides. Tidal currents are strongest near the shore, in bays, and in estuaries along our coasts. This illustration will give you an idea of how it works. As the tide rises, water moves inland. This is called a flood current. As the tide recedes, the water moves seaward. This is called an ebb current. You can see the movement of water here by watching the green seaweed move back and forth. Now let's zoom out and look at what's happening near the surface of the ocean on a global scale over time. At this scale, currents are driven primarily by two different forces. The first force is something we all know: the wind. This animation is from NASA's Goddard Space Flight Center. It shows surface ocean currents around the world during the period from June 2005 to December 2007. Check our show notes for a link to the full animation. Now let's take a few moments to look at a few prominent surface ocean currents. Do you see that? You've probably heard of this current. It's called the Gulf Stream. It transports nearly 4 billion cubic feet of water per second. Now let's speed up a bit and go look at another special current. Coming into view now is the Kuroshio Current. It's located off the east coast of Japan. This is the ocean's largest current. It can travel between 25 to 75 miles a day and is equal in volume to 6,000 large rivers. Surface ocean currents on the open ocean are fantastically complicated and beautiful. They're driven by a complex global wind system. But there's one more ocean current force that you may have never heard of. It's called thermohaline circulation. Thermo means heat, and haline refers to salinity. This term describes how changes in heat and salt content constantly change the density of ocean water. Cold, salty water is dense and sinks to the bottom of the ocean, and eventually this water returns to the surface through mixing and wind-driven upwelling. On a global scale, the sinking and rising of ocean water creates what scientists call the Great Ocean Conveyor Belt. This belt affects the Earth's climate by driving warm water from the equator and cold water from the poles around the Earth. It takes water almost 1,000 years to move through the whole conveyor belt. So there you have it. Tides, wind, and heat and salinity are all factors that put the motion in the ocean. This is Making Waves from NOAA's National Ocean Service.
Okay, so now we know that in the deep ocean, on the slope and the continental rise, that deep ocean currents are driven by thermohaline circulation. We've seen thermohaline circulation before when we talked about the Gateways to Glaciers lab. The surface currents are moving warm water around the Earth, while deep water is moving cooler, dense, salty, cold water around the Earth. And these deep ocean currents disturb sediments in the deep ocean on the slope and the continental rise. These relatively slow-moving currents, between 5 and 20 centimeters per second, will disturb some of the fine-grained sediments that are found on the slope and the rise. So this represents what a contorite might look like in the rock record. You would have muds from your normal background sedimentation of fine-grained material settling out of suspension, with some indistinct lamination because it's nice and thoroughly bioturbated by all the organisms that are enjoying the organic material among the mud. Here you have some silt models and lenses of silts, some irregular layers. Bioturbation continues with some variable contacts. So the contacts between the silts and the muds, that's what that's referring to. And this is changing because we're seeing an increase in the velocity of the current. So it's now able to carry and deposit some more silts. At the maximum velocity of the current at 5 to 20 centimeters per second, we're going to get more silts and even some sands. So it's going to be more massive with some irregular sandy pockets. There'll be bioturbation because you're bringing in fresh sediment, fresh organic material, and oxygen on these currents. And there could be some sharp contacts between the underlying sediment and the sandy silt that's being carried in on this current. And as the current velocity decreases, you start to return to the previous types of sedimentation that you've seen before. The other thing that can form these contour currents is geostrophic flow. So the Coriolis effect is based on the spinning of the Earth and the changes in density of fluid flow, and these geostrophic flows move parallel to shoreline. And so this will also disturb the sediments on the slope and the continental rise. If the current is strong enough to keep mud in suspension, then you're only going to get those sands and silts deposited at that maximum velocity point. You also have potential for some sedimentary structures here. You might get some crossbeds, some ripples that will form, and maybe some of the other secondary structures we've spoken about before as well, like flame structures and ball and pillow structures if the sedimentation happens rapidly enough and there's compression. The ichnofacies that we're going to see on the continental slope and the continental rise is going to be the Zoophycus ichnofacies, which is characterized by just a few particular genera or ichnofauna, the Phycosiphon, the Zoophycus, and the Spirophyton, among others. The last thing we want to talk about in regards to the slope and continental rise are submarine canyons. Submarine canyons bisect or cut into the continental slope. And one of the most famous submarine canyons is the one right here in Monterey Canyon. Submarine canyons are the result of sea level fall, like during the last glacial maximum, for example, that allowed rivers to form on the continental shelf that was exposed as sea level fell. So it starts to cut into the continental shelf and cut down into the slope. Then as sea level rises, the river is drowned and becomes a submarine canyon. Submarine canyons are really important because they control the flow of sediment off of the shelf out into the slope and the rise. So it's a great way to bring coarse-grained material farther away from the shore, to bring organic material from rivers and deltas farther out into the deep ocean for organisms to thrive on. So submarine canyons can be a place where we see a lot of organisms living in very deep conditions because of the nutrients and oxygen that are transported to the deep through the flows that happen in these submarine canyons. Just like we talked about how canyons channelize the flow, and then we have alluvial fans deposited in the basin as channelized flow deposits at a fan shape once the fluid flow decreases as it opens up into the basin. We see the same type of structures related to submarine canyons. Submarine canyons channelize fluid and sediment flows that allow for the deposition of submarine fans. As you move from the confined flow that's in the canyon to the unconfined flow that's on the slope or the rise, it allows you to construct lots of layers of turbidites interlayered with mud deposits, and so you'll get the same kind of structure as an alluvial fan, but deep out in the continental slope or continental rise. Here's an image from above of Monterey Canyon. Here's Moss Landing. You might be familiar with the Moss Landing Marine Lab, part of the San Jose State campus, that's located here on Monterey Bay. And this is the beginning point of the Monterey Canyon. It's narrow and deep and channelized, and then as it cuts through the continental shelf, the continental slope, it opens up onto the continental rise and onto the abyssal plain. We're going to watch some videos on Monterey Canyon. specifically watching some of the turbidity currents that flow through Monterey Canyon and some very recently developed animations of what the canyon geomorphology looks like.
Monterey Canyon is really one of the great submarine canyons of the world. It runs out over 470 kilometers, meandering all the way out into the deep abyss.
If you drained the Monterey Canyon, it would look very similar to the Grand Canyon, with meandering channel with high, steep walls and sand deposits in the middle of the channel.
We know the surface of other planets better than we know the surface of the Earth in the deep ocean. And for the most part, it's true because it's so much harder. The ocean is in the way.
I think this animation allows the public to get a sense of the grand scale of Monterey Canyon and to start to see and appreciate this massive feature that's right in our backyard.
Every time we go out, we're mapping something that hasn't been mapped before. We're seeing things that haven't been seen before. We're exploring. We get to explore.
We want to understand how Monterey Canyon formed, if, when, and how it's changing over time. And the maps are the first step to beginning understanding those processes.
We map at a meter scale or meter resolution. We fly the AUVs at a 50-meter altitude, and we're using this multi-beam sonar that pings 3 times a second. And every time it pings, it gets a set of soundings, a set of depth measurements. Every one of those soundings has a footprint that's just about a meter across, and that's why we say it's meter scale mapping. If we have a feature that's about a meter in size, we will actually see it in our map.
So when we can map the seafloor at this 1 meter resolution, we can start to see and understand faults, unique biological habitat. We can start to begin to understand what processes are occurring in the canyons and how sediment is being transported across our globe.
With this fly-through, you're seeing the data from the AUVs. Come here, and we'll just stop it right there, and you see those bands there. This is a glacier of sand that actually moves really fast and really suddenly and then stops and leaves behind these features. Submarine canyons like Monterey Canyon form the most important conduits of material from the continents to the abyss. Moving material from land to the abyss, you're moving carbon all around the world. It's a huge part of the carbon cycle, and so here we have an opportunity to study these active processes, but they're globally important. They're not just important here in coastal California.
I think it's very cool to know that we have something just like the Grand Canyon right off the coast from Santa Cruz and Moss Landing and Monterey. This Monterey Canyon, this submarine canyon, that's full of beautiful and very interesting life that we saw in those videos, and unique sedimentary deposits like these turbidity currents that we've been speaking about. So as the sediment is chugging down that submarine canyon, when it enters out onto the abyssal plain as shown in the video, we might get a submarine fan. So again, these submarine fans are forming as confined flow from the canyon goes to an unconfined system out on the continental slope and the continental rise. And so these submarine fans are going to be constructed from multiple layers of turbidites and the intermediate muds that are going to be settling from suspension. So here's a question for you. What kind of structure do you think these submarine fans are going to have? Are they going to coarsen upwards or fine upwards? What other fan-shaped deposits have we talked about in this class so far? And what has the stacking pattern been for those deposits? Things like deltas and alluvial fans have a similar structure. So we can start to make comparisons between all of these systems that behave similarly, that have first principles in common. moving from the confined flow of a canyon or a river to the unconfined area that is the basin, where there's lots of space for all the flows and the sediments to spread out and become deposited. So just like our alluvial fan, we have a proximal fan, a medial fan, a distal fan, and the normal basin. So that would be the continental rise or the abyssal plain, depending on how far this canyon cuts. So does this fan facies coarsen or fine upwards? Here's a hint for you. It's a fan, right? So go back to your notes about deltas and alluvial fans to figure that out. I'm just going to walk through some of the different parts of the fan that we might see. There are a lot of details here that I'm not too worried about you remembering. I'm just going to put some of the highlights for the different types of dominant deposits or processes that we see in each of the environments. The basin plane, the outer fan, the middle fan, the inner fan, and the slope. So you could compare the outer, middle, and inner fan to the outer, middle, and inner parts of a delta, or the outer, middle, and inner parts of an alluvial fan. What a great question to put on an exam. So the basin plane, again, is going to be the abyssal plain or the continental rise. And so this area is dominated by pelagic sedimentation. Pelagic is our word that describes the open ocean. This is going to be muds that are settling out of suspension. So laminated muds and silts are our pelagic sedimentation. The second most common type of deposit that we'll get in the basin plane are turbidites, so the last gasp of the turbidite that extends the furthest out into the basin plane. And then maybe some slumps and debris flows that could reach that far, but they're the least important. It's primarily this pelagic sedimentation. And you can see that here. It's mostly these gray muds that we're seeing, and some occasional coarser material from turbidity currents or slumps and debris flows. The outer fan is dominated by turbidites. That's the primary sediment type that we're seeing here. So you're seeing more of this coarse material. The secondary types of sediments are going to be pelagic, so our background sedimentation, and some slumps and debris flows. And more pelagic sedimentation becoming important in the outer fan deposits. So again, you'll see a lot of that mud here, but also turbidites that make it out that far. The middle fan is really dominated by turbidites, and you can see them here with the flute casts as they're scouring the previous deposits, so these thick turbidite deposits. The second most important are going to be debris flows and slumps that occur on the middle fan. This is going to be a steeper portion of the fan compared to the outer section, which would be much less steep. But there's still pelagic sedimentation that's important here. That's breaking up the turbidity flows and debris flows that carry coarse sediments out into the middle of the fan. The inner fan has a lot of pelagic sedimentation actually. Because it's really channelized in this area, it's going to be transporting more of the coarse-grained material out into the middle fan before it gets deposited. And then we have a lot of slumps and debris flows. Those are going to be very important. So you can see these very thick deposits of very coarse-grained material from this cohesive matrix-supported debris flows that form here. And then the third most important are the turbidity currents, because they're really passing by the inner fan. They have a lot of momentum here, and they're just moving through. And they're losing their momentum out here on the middle fan, which is where we primarily see our turbidites. So it's actually pelagic sedimentation, slumps, and debris flows that we see in the inner fan. That's quite similar actually to our alluvial fan deposits, where we also get more debris flows in the proximal section. And then our slope deposits, again, are dominated more by pelagic sedimentation. Here, as in the inner fan, the turbidity currents are passing through, and so we get more of that background mud that's settling out. And then finally, slumps and debris flows are very common on the slope, as we've discussed before. This figure here shows some of the submarine fans that are found off the coast of many major rivers. It says here each deepwater fan is unique, and it has a unique internal structure, elements, and lithology that depend on the scale of the fan and the response to local processes of the depositional setting. So differences in the tectonic setting, the source terrain, so the type of sediment that we have, and the physiogeography, how steep is the surrounding continental terrain, and the slope and the continental shelf itself is going to control the type of submarine fans that you get. So here is our Monterey fan represented here, and we can compare that to the fans that are found off the Mississippi River and the Amazon. These are both formed on passive margins, so you can see how broad these fans are because there's a lot of continental shelf space because there's not a tectonic fault or tectonic uplift occurring alongside the Amazon River or the Mississippi. This allows for a lot of sediments to accumulate in these subsiding basins on passive margins that are not tectonically active. And then you can see a variety of these other fan deposits that are formed from other river systems depositing out into the ocean. So let's take a pause at the end of this lecture for you to think about the sloped and continental rise deposits we've thought about so far. What are the main sediment types that we see in the slope and rise? What are the common sedimentary structures? I'll give you a hint. Turbidites are really important in this environment. Then do a bed-to-bed comparison. Do these sediments tend to coarsen or fine upwards? It kind of depends. Are you looking at a submarine fan? Are you looking at a turbidite? Or are you looking at a contorite? We've looked at a couple of different types of facies models for the slope. So go back and refer to those and figure out, do they coarsen or fine upwards? Are there major unconformities in these bed-to-bed comparisons? And then finally, how laterally continuous or discontinuous are the sediments that are deposited on the slope? The last thing to think about before we close out is to start to think about stratigraphy. We're going to start to transition from learning about different facies into stratigraphy in a couple more lectures. Things that help us figure out when different events happened in the deep ocean include things like biomarkers, particular organisms that lived in a certain time that we can correlate or match up between different rock units to be able to say that these two different rocks were deposited at the same time. Another great marker is volcanic ash deposits, which is shown here, a plume of ash that's then settling into the deep ocean and is going to form a blanket that represents one time interval. Pelagic limestones, so things like foraminifera and other carbonate-based organisms that live in the deep ocean can settle down into the sediments of the continental slope and rise and make great stratigraphic markers for us to be able to correlate to figure out how old our rocks are. So this is just a little tidbit for you to start to think about how we can figure out which rocks were deposited at the same time and what mechanisms we might use to do that with.